Swayam Prabha. Digital India. Educated India.
Hello. So welcome to Astrochemistry. This is lecture 20. And as a quick recap, in the previous lecture, we looked into the idea that the spectrum of sun exhibited several dark lines. Now, on Earth, right? On Earth, it was noticed that when elements absorb light, you get dark lines. Likewise, when elements emit light, you get bright lines. And for any given element, the wavelength of absorption was found to be the same as the wavelength of emission. Alright, so this is what we had figured out. And we also saw that, the bright lines that were obtained from emitted light from elements had the same wavelength as some of the dark lines noticed in the spectrum of sun. Okay, and we've also shown that the same element on Earth, right? When we record its absorption spectrum, at the same wavelength, you get a dark line. So what does it tell you? Taken together, what does it tell you? I'll just also write it down on the board. Okay, right? The lambda absorption. Okay. I'll just call it as lambda A. Instead of writing it absorption and emission every time, and this is going to be E. Okay. Lambda A on Earth, okay, right, is equal to lambda E on Earth. Okay, the second E stands for Earth. This is for emission. I'll put it EM to avoid confusion with Earth. Okay, and it was also noted to be the same as the wavelength for the dark lines, right? The lambda obtained from sun. Please notice this for the dark lines. Are we all good with the sequence of experiments? So on sun we recorded something, we got some dark lines. On Earth we got some dark lines and bright lines for the same element, right? And we noticed that the wavelength of the dark lines is going to be the same as the wavelength of the bright lines for the same element. Okay, so which tells us that when light is absorbed by an element, right, you get the dark line, whereas when light is emitted, you get the bright line. Okay, so and exactly the same wavelength of absorption and emission noticed on Earth, you match that with the wavelength recorded on sun. Isn't it fascinating? You do an unrelated experiment on Earth, right? And you find that the exact same experimental observation is also obtained from the sun. What does it tell you? Any guesses? What does it tell you? What does it tell you about the nature of the sun? Well, this tells you that. Any ideas and any thoughts? What exactly does it tell about the nature of the sun? The sun, okay, right, is also made up of same elements present on Earth. Now, this is a massive, 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 massive leap of understanding. Okay, right? This is a massive leap of knowledge. For a long time, what was the sun thought out to be? The sun is a celestial body. Yes, celestial is fine. But hey, it is no longer mysterious. It is not this mysterious mythical entity, okay, but it is something that just consists of elements present on Earth. And how did we figure it out? By matching by recording the spectrum of sun and matching the lines with the elements present on Earth. Are we good? So this is a very, very important observation, and it tells you that even in the celestial bodies, you have the same elements that are present on Earth also. Okay, so this is an exceptionally important observation. In fact, this particular series of events, can be called as the birth of astrophysics, which is a precursor to astrochemistry. Because for chemistry, right, we're only talking about elements and atoms now. I mean, what are elements? They're all atomic, right? But for chemistry, we need to go one step further and see how molecules may be observed in space. We have now seen how elements or atoms can be observed in space, right? To begin with, right, we just saw an example of how atoms or elements are observed in the sun. You know that, okay, the dark line is due to some element on Earth. So if you get the dark line at the exact same wavelength in the sun also, well, the sun should also be containing the same element. Are we clear? Okay. Now, notice this. As of now, there are still, quite a few unanswered questions in this whole sequence, starting from lecture 19. I will, connect all those loose ends and give you, in the form of question answers, a succinct summary. Okay. It is that why is solar spectrum, the spectrum of sun, almost continuous? The answer is the sun emits light of all wavelengths and frequencies, all lambdas, correct? In fact, the VIBGR, that is just a minor portion of the electromagnetic spectrum. There is an entire range, both on this side of the violet and that side of the infrared radiation. You have what are called as X-rays and gamma rays, and you have what are called as radio waves, this side, okay? So the sun, of course, emits light of all wavelengths. We are able to, see only the visible part, okay? But why is it only almost continuous? It's only almost continuous. Why only almost? The answer is elements, the same elements which are present on Earth, okay, right? Elements, in sun or the sun's atmosphere, okay? Atmosphere absorb light, and this results in the spectrum not being exactly continuous, but there are some dark lines noted. Okay, that's it. I have a few more questions though. Interestingly, along the same lines. The next question is that why are these lines dark? Why are absorption lines dark? Well, what is the answer? Well, if you imagine light to be some entity, right? That light is actually absorbed. Light is absorbed by a molecule, okay? Because light is absorbed by the element. And that is why you see them as dark lines, okay? Light is absorbed. And so, when light is absorbed, what do you get? What is the opposite of light? It's darkness, right? So therefore, you get dark lines. The next question would be that, it's a natural opposite question, right? Why are emission lines bright? Well, the answer by now should be obvious, correct? What is the answer? The answer is that they are bright because light is emitted. By the element. Okay, so light is emitted by the element. So when light is emitted by the element, we understand that, there is light. Okay, so that is why it's a bright spot. So absorption results in dark lines and emission results in bright lines. Now, the next question that we shall be addressing is, this is a rather profound question, okay? And I'm not going to give you a complete answer now. The question is, why are these lines discrete and occur at specific wavelengths? Now, this is a profound question. The last 4 questions, right? Why is it continuous? And then why only almost? And then why dark, why light? Well, from the ongoing discussion itself, we could understand. But this question is a very profound question. Although you must have studied about it in your high school and some college chemistry and physics, this is the profound question. Can you guess why? The question is, why is it discrete? Okay, right? And why do they occur at specific wavelengths? Now, what is the opposite of discrete? Something that's continuous, right? For example, the solar spectrum is almost continuous. You see all wavelengths of all colors. But here, it is not a continuous stretch. It is one specific line. Why does this happen? Well, I'll give you the short answer. Okay, I won't call this answer. I will call this like short answer. The short answer is, it is due to quantization of bound systems and quantum mechanics. So, of course, this may not have been pretty much explanatory, but you all know that, even from your, and most likely in all the state boards in the CBSE and ICSE syllabi, you talk about the hydrogen atom spectrum being discrete lines. And that discrete lines is due to quantization, correct? So, more details will be taught to you, in the same course when we discuss the relevance of quantum mechanics for astrochemistry. Okay. Now you already see that, hey, astrochemistry is a highly interdisciplinary subject. We've been covering topics ranging from physics, physical chemistry, organic and inorganic chemistry, and now look at what is coming into the picture. Spectroscopy, and now, most recently, quantum mechanics. So, more coming soon. So the long answer is coming soon. So please hang on to it, and I shall explain to you in greater detail. And what is the last question? The last question that I'm going to be asking in this series to make you understand what exactly is happening here is, what is the clinching evidence that sun is made of, or sun contains, okay, right? Elements on Earth. The answer, in short, is the long answer, of course, I've been giving you in the past 2 lectures. The short answer and the crisp answer is that the clinching evidence is that the lambda of the dark lines from the sun is the same as the wavelength of the dark lines. The absorption lines. The absorption lines are going to be dark. We know that. The absorption lines noticed on Earth, which is the same as the wavelength of the emission lines noticed on Earth. So therefore, we know that, these are from the same elements. Which means that this also has to be from the same element. All right. So now, therefore, we understand that the sun is made up of elements present on Earth. Now, this marks a very epochal discovery. This is an epochal discovery that, hey, celestial bodies can also be studied in the same way we study terrestrial objects. Okay. Now, before we proceed further, I'll just give you one important and key information about this whole what is present in sun story. Okay. Now, we saw that like the solar spectrum featured several dark lines. Okay. In fact, in using modern telescopes, going way beyond Fraunhofer's time, we can notice tens of thousands of such dark lines. Okay, because there are so many atoms and so many ionized states in the sun, and so they all give specific absorption lines. Okay, so now the question answers have been completely sorted. Okay, I'll just give you one real cool fun fact from the elements found on sun. So in fact, from the Fraunhofer's lines, okay, Fraunhofer's lines. Now, from Fraunhofer's lines, people also found, a specific line, a specific dark line. We're talking about in the 1830s, okay, for which there was no analog on Earth. So what could this celestial mysterious species be? So people had to wait for until 50 years, okay, approximately in the 1880s, I believe by William Ramsay, okay, around 1880s, people on Earth discovered a new element called as helium, and its spectrum matched with the unknown line, matched exactly with the unknown line from sun. And so what does this information tell you? Well, it is not just that you understand what is present on sun based on what is on Earth. You also get to know about what is on Earth by discovering, what is present in the sun. And this element and atom helium was actually first discovered in the sun. And that's in fact why it is called as helium. Helios for Greek, has some reference to sun. I don't know exactly, but yeah. All right. So isn't it fascinating? Through this entire exercise, by just understanding the properties of light and what happens, when elements, the kind of light they emit, approximately 200 or 150 years ago, we were able to find out so many scientific aspects. So this whole procedure, right? This whole procedure of finding out the unknown in a completely different region of space, right, from the known, beautifully illustrates the scientific procedure and the interdisciplinarity of science. You're talking about heating elements, which is chemistry, and recording a spectrum, which is physics, and this beautiful idea in chemical physics or physical chemistry, which leads to this amazing story of astrochemistry. All right. So much for how the elements are detected in the sun. Okay. Now we'll go back to the fundamental question that we asked. What was the fundamental question? Through this illustration, I'll call this page 8. What was the bigger question? Where were we? The fundamental question is how to detect molecules in space, right? So this was the question. This was the question that was being asked. How do you detect molecules in space? And through this illustration that happened, molecules are atoms. We're still not looking into molecules. For now, we have looked into definitely atoms, correct? So how do you detect molecules, atoms in space? What do you do? Through the sun, earth, the Fraunhofer, Bunsen, Kirchhoff experiment, the bright line, dark line, through the whole story, what do we come to understand? We understand that answer is A, first, get some light. Literally, not just figuratively. Okay, get some light from space. Okay, right? Get some light from space. And B, on Earth, measure the obtained light's wavelength, frequency, and the wave number, all of these, especially looking for discrete lines. Okay, so you get, so for example, in the sun's experiment, we got the light from the sun, and then we recorded its spectrum. And on Earth, you measure you get light, right? Once you record its spectrum, you look for, like various discrete lines, because, in a continuous stretch, right, it is difficult to identify too many things. But once you get discrete lines, you understand that how we may be talking about specific molecules. Okay, correct? So you do this. But there is one more step. It doesn't stop here. Can you guess what the next step is? See, the next step is going to be, it is not sufficient if you measure it. You should measure it and recall from the same sun story. From the sun story, what did we do? We measured it for samples present on Earth. So compare with the wavelength, the frequency, and the wave numbers, right, for molecules bar atoms present on Earth from their spectrum. So this is in a nutshell. This is the overall simplified idea. The broad idea is as simple as this. So for this, to get some light from the space, right, you need advanced telescopes. Okay, because we're talking about obtaining light from very far away objects. This is the first point. And subsequent to that, you measure, the wavelength, the frequency, and then the wave numbers of specific discrete lines obtained from this spectrum. Okay, and you compare with, what is known on Earth. You compare with various molecules or atoms present on Earth, and hey, if they match, if they exactly match, you know that you understand what is present in space. Are we clear? So look at what a powerful idea. Look at what a powerful idea this concept of spectroscope gives us. Okay, in fact, the whole branch, okay, right? The whole branch of spectroscopy, right? When combined with telescopy, the whole area is called as radio astronomy. Approximately in one or two lectures subsequent to this one, we shall be looking into that area, okay, called as radio astronomy. So we can actually detect all the molecules in space. And this is more or less, the same procedure via which all the molecules we discussed, starting from, molecules as exotic as SiO or like MgNC to all the way up to C3H and also C60, right? Or for example, the cyanonaphthalines or cyanobenzene. For all these molecules, they were all detected by following the exact procedures. And of course, this is just a simplified idea. There are going to be so many details. There are going to be so many details to in each of these steps. And all those details are what we shall be looking into the rest of this course, along with some fundamental ideas from physics and chemistry. Are we clear? Okay. On that note, the next concept, I want to familiarize you with in this lecture is going to be the, I'm sure you all know about the electromagnetic spectrum, but so time is now ripe. Okay, now that we understand that, we measure the properties of light, and from that we detect molecules. It is now appropriate time to start discussing about the electromagnetic spectrum. Okay, so the electromagnetic spectrum. Now, what I'm going to start with is, I'll first give you, the various ranges. Just like we saw in the interstellar medium, right? There are different regions. Now, the electromagnetic spectrum is also not homogeneous. It comprises of different types of electromagnetic waves. Okay. Now, I'll give you the wavelengths of all these regions. Okay, in order of increasing energy. Okay, right? And from that, you'll have a rough idea about the energies associated. And in the subsequent lectures, we shall map out the processes occurring in each of these regions. Okay. Say, for example, there are some waves called as radio waves. Now, the wavelength for this region, is actually going to be greater than 10 to the power minus 1 meters. Okay, the wavelength is measured in terms of meters. Okay, right? So these are called as radio waves. So after radio waves, you have the microwave region. This is where, in fact, a lot of rotations of molecules happens. So in the microwave region, the wavelength ranges from 10 to the power minus 3 to 10 to the power minus 1 meters. The next region is going to be the infrared region, which is where a lot of molecular vibrations and rho vibrations, rotation plus vibration happens. Now, this is going to be in the order of 7 into 10 to the power minus 3 meters to 10 to the power minus 3 meters. The next region is the visible region. People also call it as the the region for optical spectroscopy. Okay, right? And the wavelength for this region is going to be of the order of 400 nanometers. That is 4 into 10 to the power. There's a small mistake here. This should be 7, right? I'm talking about 700 nanometers. So the IR is a huge stretch. Okay, so the visible range is going to be 4 into 10 to the power minus 7 to 7 into 10 to the power minus 7 meters. All right, so this is the visible optical range. The next range is going to be your ultraviolet region. Now, the ultraviolet region is going to be somewhere between 10 to the power minus 8 to 4 into 10 to the power minus 7. Okay, this is the range for the UV. The next region is what is called as X-ray. Now, these are very high energy waves. Okay, the wavelength is going to be of the order of 10 to the power minus 11 to 10 to the power minus 8. And then you have the gamma rays, which are extremely powerful vis-a-vis the radio waves. Okay, and they have a wavelength of less than 10 to the power minus 11 meters. So I'll just verify if the numbers are correct. For radio waves, it's 10 to the power minus 1. This is 10 to the power minus 3 to 10 to the power minus 1. For the infrared radiation, it is 7 to 10 to the power minus 7 10 to the power minus 3. So in fact, the IR region itself, right, can be decomposed into several regions, the near IR, far IR, etc. And the range is a lot. Okay. Then the visible region is a very tiny fraction of approximately only 300 nanometers. 4 into 10 to the power 10 to the power minus 7 meters to 7 into 10 to the power minus 7 meters. The UV region is of course ranging from 10 to the power minus 8 to a few hundreds of nanometers. And what follows, that is X-ray, all the way up to 10 to the power minus 11, and gamma rays, which is less than 10 to the power minus 11 meters. All right, are we good with this? Now, as a homework, okay, I ask you to find out the frequency of all these regions. How would you do this? This is going to be a homework, and the next homework is also going to be finding the energy using the formula hc over lambda, right? Well, h is the Planck constant and c is the speed of light, and you can fill these two columns. Are we clear? So in this lecture, that is lecture 20, we finished looking at how exactly, in a nutshell, the simplified version of how molecules can be detected in space was discussed. And this was followed by an introduction to the electromagnetic spectrum and the span of various regions, noting that the visible or optical region is a very tiny fraction. On that note, we end this lecture, and in the next lecture, we shall see how molecules are detected in space beyond just atoms. Thank you.